take a minute and randomly mark 5 of the boxes in this 16-box grid to the left. Have you got them marked? Okay. Are the boxes, the way you mark the boxes more similar to the grid on the left or the grid on the right? Probably your boxes are more randomly scattered like the ones on the right that I have marked here. But these are actually not a result of a random process. I just marked these myself like you just did. But when I did a true random process on my calculator, I numbered the boxes on the grid 1 through 16, going across the rows 1, 2, 3, 4, 5, 6, 7, 8, etc. And I randomly generated 5 numbers from 1 to 16 on my calculators. And I got the numbers 3, 11, 13, 14, and 16. And those are the boxes I marked. So this grid is a truly random process, whereas this was just my thought of what a random process would look like. And actually, each of those are equally likely to occur if I randomly generated 5 numbers. But when we mark things randomly, we automatically assume that they're going to be fairly evenly scattered. And this is definitely not evenly scattered, yet it is just as much a random process as this would have been if I'd picked those 5 numbers randomly. Now let's look at a lottery game. In the Pick 4 lottery game, 4 numbers between 0 and 9 are randomly generated, repetition being allowed, to give you a 4-digit number. So we're going to simulate picking the winning number. Now, when you play the game, you write down the 4 numbers you think are going to be the winning number, and obviously if you match, you win. So if we did this on our calculator, we do randint. I'm just going to go ahead and copy my randint, and it would be from 0 to 9, 0, 9, 4. Okay, so here's some examples of winning numbers. So that would be 8, 6, 4, 3, 2, 5, 8, 5, 3, 2, 7, 9, 6, 5, 0, 0, 0, 4, 0, 7, etc. I guess we're going to have to assume that the first number could be 0, even though that's not a 4-digit number. Otherwise, they wouldn't all be equally likely. So here's some examples of possible numbers that could be generated. So let's go back here. Which number do you think would be more likely to win? Like if you were to pick one of these 2 numbers to play the game, this lottery game, which would you be more likely to pick? Now, having seen the numbers that I just generated in the calculator, 2873 seems more likely because 9999 seems less random. But in actual fact, 9999 is just as likely to occur as 2873. It is just as random as 2873. But our intuition tells us otherwise. Now let's look at another situation where people maybe don't have the best intuition about randomness. This is in your book on page 295. Aren't we due for a boy? It says, don't fall for the law of averages. So the law of averages doesn't guarantee me a girl after 7 straight boys, but can't I at least get a group discount on the delivery fee? Belief in this phony law of averages can lead to serious consequences. A few years ago, an advice columnist published a letter from a distraught mother of 8 girls. She and her husband had planned to limit their family to 4 children, but they wanted to have at least 1 boy. When the first 4 children were all girls, they tried again, and again, and again. After 7 straight girls, even her doctor had assured her that the law of averages was in our favor 100 to 1. Unfortunately for this couple, having children is like tossing coins. 8 girls in a row is highly unlikely, but once 7 girls have been born, it is not at all unlikely that the next child will be a girl. And it was. Just like tossing a coin, 8 heads in a row would be unlikely, but having tossed 7 heads, it's just as equally likely that the next coin would be either a head or a tail. It doesn't change it. The law of averages makes us think that previous events will affect the next event, when really that doesn't always happen in probability. Let's take a look at page 301, number 12, for some other fallacies that people have about probability. A gambler knows that red and black are equally likely to occur on each spin of a roulette wheel. He observes 5 consecutive reds occur and bets heavily on black at the next spin. Asked why, he explains that black is due by the law of averages. Explain to the gambler what is wrong with this reasoning. Well, if black and red are equally likely to occur, then the fact that there are 5 consecutive reds does not affect at all the next spin. Human beings tend to think that that if you have a bunch of things happen in a row, like 5 heads in a row, or in this case 5 reds in a row, the next one needs to sort of balance things out. The next spin or the next toss needs to balance things out, when in actuality that is not at all true. Each individual event is random and is not affected by the previous ones in this case. So you convince the gambler, and so he goes to this next thing and saying, after hearing you explain why red and black are still equally likely after 5 reds on the roulette wheel, the gambler moves to a poker game. He is dealt 5 straight red cards. He remembers what you said and assumes the next card dealt in the same hand is equally likely to be red or black. Is the gambler right or wrong, and why? Well, this is a different situation. When the roulette wheel is spun, each individual spin is independent of the other ones. Each time red and black are equally likely to occur. But when you are dealing out a deck of cards, the deck has only 52 cards in it. So once you've dealt out 5 straight red cards, then red and black are no longer equally likely to occur, because now out of the 26 red cards, 5 have already been used, so there's only 21 reds left, but there's still 26 blacks left. So now it is more likely that the next card is a black. This is a situation where each card is not an independent event. Each one does affect the one after it, because there are a limited number of cards and it doesn't just reset every time. Now, if you dealt the 5 cards and then put them back and shuffled, then yes, the next time it would be equally likely to be red or black, but not in the situation that we see in Part B here. So to sum up, our intuition about randomness is often wrong. Randomness is predictable in the long run, but our intuition, that's supposed to say our intuition, tries to tell us that randomness is also predicted in the short run, that things should, quote, even out even in the short run. We believe myths like the hot hand or the winning streak or the law of averages, which make us think that an independent random event can be influenced by previous outcomes. For example, when people are gambling or seeing a particular hot hand in a basketball game, for example, with some players making shot after shot, we tend to either think, well, their person's on a winning streak, or they've got a hot hand in shooting and it's going to continue because they're on a winning streak. Or we tend to think, well, things are going to even out. They can't keep doing this forever. There's been so many wins that we're certainly going to get a loss now. So we tend to think that things should even out even when each event is completely independent of the previous event. So we can't trust our intuition about randomness. It's often wrong.